Hello, dear learners! Good morning! I am Teacher Charlene and welcome to a day that fills with fun and learning. So get your pens ready, your paper or notebook, and your self-learning module in General Chemistry 1, Quarter 1, Module 5. In this lesson, you are expected to define pressure and give the common units of pressure. In the previous module, we focused on the microscopic properties of matter, the properties of individual atoms, ions and molecules, and how the electronic structure of atoms and ions determine the stoichiometry and three-dimensional geometry of the compounds they form. We will now focus on macroscopic properties, the behavior of aggregates with large number of atoms, ions, or molecules. An understanding of macroscopic properties is central to an understanding of chemistry. Why? For example, are many substances gases under normal pressure and temperature 1 atmospheric pressure at 25 degrees Celsius, whereas others are liquid or solids? We will examine each form of matter, gas, liquids, and solids, as well as the nature of the forces, such as hydrogen bonding and electrostatic interaction that hold molecules and ionic compounds together in these three states. So let's define some concepts. Gas. Gas is a state of matter where the molecules are far apart, assumes the volume and shape of the container, most compressible state of matter, and tend to expand indefinitely. Gases apply pressure to any surface that it will have contact since molecules are continuously moving or constantly in motion. Pressure. Pressure is the force per unit area. It is the force that is exerted by the gas. It is determined by the flow of a high-pressure region to a low-pressure region. One example is when you blow a balloon. The balloon will expand because the pressure of the air inside the balloon is greater than the outside. As the balloon continues to expand until it reaches the limit of the amount of air that it can hold, it will eventually pop. Now, it is due to the pressure exerted by the air against the wall of the balloon. Since the balloon cannot hold the amount of air and it is continuously exerting force against the wall of the balloon, it will pop because the walls of the balloon is high enough to the amount of pressure that it can handle. Learners, let's watch this video to understand more about pressure and temperature of gases.
Who didn't like playing in ball pits when they were a child? Now let's imagine a room filled with these balls constantly moving around in different directions. This is how molecules in a gas move. In this video, we're going to discover more about amazing gases and the effect temperature and pressure have on them. Have you ever wondered why the cork explodes out of a champagne bottle? Or the fizz when you open up a shaken bottle of Coca-Cola? This is all to do with gas and pressure building up inside the bottles. So let's have a look at pressure in gases in a little more detail. Gases exert a pressure on any surface which they are in contact with. The more particles that hit the walls of the container, the higher the pressure, like when you shake a Coke bottle, and as it fizzes, the bottle feels harder than before. This is the gas particles pushing against the plastic bottle. So we have the equation. Pressure is force per unit area. We also see the effect of pressure in gases when we blow a balloon up too much, and it pops. This is because we've increased the pressure of the air molecules pushing against the rubber balloon too much. Heating also increases pressure. Why is that? As a gas is heated up, the particles gain more energy and move around more quickly. They then hit into the walls of the container harder and more often. This understandably increases the pressure, and if the pressure is too great, the container can burst. Again, think of popping balloons and bursting tires. Ever read on your deodorant can a warning that says not to leave it in the sun? This is because inside the can is a gas, and as we just discovered, heating up a gas causes the pressure to increase and can result in that can exploding. Not a good idea. So what happens if we then cool down the gas? This time, the particles have less energy, and so less pressure is being exerted on the container, which is why balloons shrink and become sad and saggy. Now, it's time for something none of us like. Needles and syringes. Thankfully, there are no injections for us today. We're just learning that needles and syringes work due to pressure in gases. When the plunger of a syringe is pulled out, it causes the volume in the chamber to increase. This increased volume causes the pressure inside to decrease. Now we have created a vacuum that wants to repressurize to normal atmospheric levels. Since it's a sealed system, except for the needle into your arm, the only fluid available is your blood, which gets sucked into the chamber. Your blood then reduces the volume, and so the pressure increases back to normal. Pause the video and fill in the missing words. Did you get them right? So there we have the effects of volume, temperature, and molecules on the pressure of a gas. I hope you enjoyed today's lesson, and I'll see you next time.
Pressure is a measurable property of a gas. To completely understand of how pressure of a gas is measured, knowing how the unit of measurements of it are derived would be helpful. First, velocity. It is the change in distance with elapsed time. Its equation form is velocity is distance moved over elapsed time, or V is equal to d over t. The SI unit of velocity is in meter per second or centimeter per second. Next, acceleration. It is the change of velocity with time, or acceleration is equal to change in velocity over elapsed time, or A is equal to V over t. The measurement used for acceleration is meter per second squared or centimeter per second squared. Another important equation to be used is the second law of motion formulated by Sir Isaac Newton, wherein force is the derived unit of pressure. It states that force is equal to mass times acceleration, and its SI unit is in Newton, where 1 Newton is equal to kilogram meter per second squared. Lastly, we define that pressure is the force per unit area, or pressure is equal to force over area, or P is equal to F over A. The SI units of pressure is in 1 Newton per squared meter, or Pascals. Atmospheric pressure is the exerted pressure of Earth's atmosphere. It is also used as a unit of pressure. The value of atmospheric pressure varies depending on the location, temperature, and weather condition, and it is commonly measured using a device called barometer. The standard atmospheric pressure is 1 atm, that is equal to the pressure that supports a column of mercury exactly 760 millimeter high at 0 degrees Celsius at sea level. There are different units used to measure pressure. Based from 1 atmospheric pressure, here are the different corresponding value
for each unit of pressure.
101,325 Pascal is equal to 101.325 kilopascal is equal to 760 millimeter mercury or 760 torr.
Here are some common compounds that are gases at room temperature.
So dear learners, please prepare your pen and paper because we will try to solve some problem. So we have two questions and you will be given 5 minutes to solve these two problems. So let's read problem number 1. A man that lives in a mountain went down to a river to go fishing. He felt a little discomfort in his ears that indicates that the pressure went up as he goes down from a high place. That day, the atmospheric pressure is measured 790 millimeter mercury. What is the value of 790 millimeter mercury to atm? And question number 2, convert 1.8 atmospheric pressure to kilopascal. So simply, the given problem is just to what? Alright, simply a conversion unit. So 5 minutes is really enough for you to solve that one. So your time starts now. My dear learners, go, go, go!
Thumbs up, learners. So let's try to solve the problem. Remember that 1 atm is equal to 760 millimeter mercury. So this conversion factor will be helpful to find the value of the pressure in atm. So the solution to be used is pressure is equal to 790 millimeter mercury times 1 atm over 760 millimeter mercury. So the millimeter mercury unit will be cancelled out, then 790 multiplied by 1 atm divided by 760. So your answer must be 1.04 atm. So the pressure is equal to 1.04 atm. Question number 2, you are asked to convert 1.8 atm to kilopascal. So a conversion of units. Therefore, 1.8 atm is equal to 0.325 kilopascal over 1 atm. So cancel out the units, atmospheric pressure. So your answer must be 182.385 kilopascal. Congratulations, learners! You did a great job today. Alright, learners, let's have some recap of our lessons today. We learned that pressure is force per unit area of surface. The SI unit for pressure is the Pascal, defined as 1 Newton per square meter. Then, the pressure exerted by an object is proportional to the force it exerts and inversely proportional to the area in which the force is exerted. Atmospheric pressure can be measured by a barometer, a closed inverted tube filled with mercury. Then, we also learned that the height of the mercury column is proportional to the atmospheric pressure, which is often reported in units of millimeter of mercury, also called torr. And lastly, the standard atmospheric pressure, the pressure required to support a column of mercury 760 millimeter tall, is yet another unit of pressure, 1 atmosphere. Great job, learners! You are indeed doing well. So that's end our lesson for today. This is Teacher Charlene. Until next time!